creating 4 open spots for bonding. By promoting a paired electron to an empty orbital, we've created 4 open spots. And that's exactly when we draw 4 dots around carbon, we're ready to create 4 bonds. So intuitively, we already knew carbon had 4 bonds, but yet according to its electron configuration, we wouldn't readily see that unless we promoted to the empty orbital. Why would we want to partner in the same room, if you will, when there's an empty room down the hall? Everybody take their own room and spread out. That's really all that term means to create a hybrid orbital. Carbon is a great example simply because it pairs the first 2 and leaves an empty orbital. Instead, we promote the 1 into the empty orbital, creating 4 open spots for bonding. That really is what this slide is trying to tell us. If carbon is a mix of all the s's and p orbitals to get 4 orbitals at the point of the corners of a tetrahedron, I'm creating 4 spots for bonding by promoting a paired set of electrons into an empty orbital. Now I see 4 spots open for bonding business. Alrighty. That's what this slide is showing. If hydrogen is a 1s orbital, carbon would be written as 2s2, 2p2. I would predict only 2 spots for bonding and leaving an empty orbital. But carbon clearly has 4 spots open for bonding. So instead, we simply promote, and that's what this slide was showing us. We promote this electron here into the empty orbital. I keep grabbing a pen with no ink. Promote that one, unpair it and promote it to the p orbital, and we come up with the boxes as we drew a moment ago, where I have 2s1, 2p3, 4 open spots for bonding. So the observed reality with 4 spots, different than the theoretical prediction if I left it as a partnered pair. Hybridization. To promote electrons into an energy level by unpartnering. So the valence bond theory, I need to check, am I on the right slide? Yep, 77. The valence bond theory has some main concepts, and let's share what those are. It says the valence electrons of the atom in a molecule reside in the quantum mechanical atomic orbitals. That's fancy for saying the s, which are spherical, the p, which are hourglass shaped, the d, which stands for diffuse, if you remember they look like clover leaves, and the f orbitals, or they may hybridize to be any kind of combination thereof. A chemical bond that results when these atomic orbitals interact, and there is a total of 2 electrons in the new molecular orbital, and they must spin in opposite directions, so the spin is the same rule. One spins up, the other will spin down. The shape of the molecule is determined by the geometry of the interacting orbitals. Some atoms hybridize their orbitals to maximize their bonding, as in our carbon example. If I can create more bonds by promoting into empty orbitals, an atom will do that. It creates stability. Hybridizing is simply mixing different types of orbitals in the valence shell to make new sets of degenerate orbitals. As in what we did here, we promoted an s electron into a p orbital. By promoting it, we created a combination of an sp hybrid orbital. If an s is spherical and a p is an hourglass, not bad for my drawing, and I take these 2 pictures and literally combine them into one, I get a combination of an hourglass and a sphere-shaped orbital. Not quite an S, not quite a P, it's between the 2. And that's what the term hybrid means, a combination between the 2 orbitals. We created, with that carbon example, a hybrid orbital known as an sp. It is between an S in energy level and the P in energy levels. So the same type of atom can have many different types of hybridization. Carbon, sp, sp2, or sp3 hybridization. sp1, P2 or P3 hybridization. Each one of those can be hybridized. So hybrid orbitals, the number of standard atomic orbitals combined, creating the number of hybrid orbitals formed. So combining a 2s with a 2p gives 2sp hybrid orbitals. On a note, hydrogen cannot hybridize. It's simply the smallest atom and can't be promoted because it only has a 1s shell. And it only has one orbital. There's nothing to promote it into. The number and types of standard atomic orbitals combined determines the shape of the hybrid orbital. And that particular kind of hybridization that occurs is the one that yields the lowest overall energy for the molecule. This sounds complicated, but it truly isn't. It really isn't. Let's just take some examples. Carbon in its unhybridized, what we would normally consider writing out 1s2, 2s2, 2p2, but I have an empty orbital. So I want to take this electron, unpair it, and promote it to this orbital here. What would we have left? We would have a hybridized orbital where I promoted this electron here. The 2p orbital are still this guy. Those are still the same. But I'm going to take this s orbital and I'm going to combine it with this empty orbital. And when I promote this electron, I create two of equal energy hybrid orbitals. This becomes an sp orbital, and this becomes an sp orbital. The 2s orbital no longer exists. If this is 2px, 2py, 2pz, think about this one still being the 2x, 2y, and the z no longer exists. These two become of equal energy. They're called sp hybrids. The two electrons that were originally in the p are still left alone. When I hybridize, promoting an electron into an empty orbital, these two now are of equal energy. They're not an s, they're not a p. They've been combined to be an sp orbital. Suppose an sp2 hybridized orbital. I can see 3 of equal energy, 1 left in a p sublevel. And sp3 hybridized. sp3 creates 1, 2, 3, 4 of equal energy levels. When we begin bonding, it's really simple, and I just call it my finger-thumb rule. If I want to know how many electron or what is the hybridized orbital, I count. And I always start with my thumb as number 1 because that's just what I've done. Find the central atom, it's carbon. How many electron domains? 1, 2. 2 electron domains. Your thumb is always the S. Draw an S on your thumb. I just did. 2 electron domains. Thumb first always. One of them will always be an S. To get two fingers in the air, a thumb and a finger, to get 2 electron domains, sp hybridization. sp, 2 fingers in the air. Down here, 3 electron domains. Carbon in the center, 1, 2, 3 electron domains. Thumb first, sp2. S is my thumb, always, always. To get 3 electron domains, I got to put 2 more fingers in the air. sp2, hybridization. Here's carbon.